Hi, everyone. Good afternoon and welcome to the first afternoon session of Catalyst Day. This is a great day when we have our Catalyst 300 students present on the collaborative group projects they have been working on all semester, coming up with solutions to problems in the world. So it's my pleasure to introduce our group today, who will be covering the development of biodegradable single-use PPE in healthcare settings. I will turn it over to them and let them introduce themselves. Thanks.
Hi, everyone. Good afternoon. I'm Ivy.
I'm Theodore Conrad.
I'm Abigail Grieger.
I'm Bradley Gill.
I'm Sarah.
And we
will be
took a look at the development. All right, so 300 million, it has been discovered that 300 million tons of plastic is being used and produced on an annual basis. The plastics being produced currently, they don't break down, they only really break up over time, and this is due to harsh weather conditions. This is a problem because the plastics make their way into our oceans as the oceans cover most of the earth. These harmful plastics contaminate and are consumed by the wildlife, the same wildlife that we rely on as food. These plastics contribute to the global greenhouse effect and are linked with hormonal imbalances as well as various cancers when consumed by humans. Next slide. So CO2 is one of the most common compound materials for the products we use today. Here are some eye-opening statistics about CO2. In 2019 alone, there were a total of 39.93 billion metric tons of gaseous CO2 emitted by the fossil fuels. In the land use change industries, CO2 is a green gas and it is a greenhouse gas and is environmentally harmful, primarily because of its ability to retain heat. CO2 alone accounts for 80% of the projected greenhouse gas emissions per EPA data. These are stats that were taken from the EPA website, and you can see it in a number form on the right in the figure.
Plastic use from hospitals has only exacerbated since the start of the COVID-19 pandemic, specifically with gloves and face masks. According to Environmental Systems Research, roughly 129 billion face masks and 65 billion gloves every month are used and disposed of on the globe. And these numbers are only increasing every year. The data on the image on the left is taken from the King Abdullah University Hospital in Jordan. This hospital is the largest in their country, and it's a little larger than the UW-Madison Hospital. A correlation can be seen between the number of patients admitted to the hospital in a 2-week period after testing positive for COVID-19 and the total amount of medical waste generated. The data from the image on the right is the amount of medical waste from gloves and face masks that were disposed of over a course of a 5-day sampling period of a large urban grocery store. As you can see, 96% of the masks were single-use items, which continue to contribute to the billions of gloves and face masks disposed of every month, continuing to harm the health of the wildlife, humans, and the earth. Altering the production, the use, and disposal of these single-use plastics can create a greener future for humans and our ecosystem.
So part of the established problem, which Theo and Brad talked about earlier, is the fact that plastic doesn't break down easily. And this is due to the fact that we need plastic to do its job a lot of the time. Now, I know that I wouldn't want gloves biodegrading on me in clinical settings. So we make gloves and other plastics really, really difficult to break down. Gloves and other plastics are established as polymers, which are materials that are often really well versed tensilely and quite elastic, that are made up of tiny building blocks called monomers. Essentially how this chemically works is we take monomers, we put them in a setting in which they can react with each other. They kind of stack up, picture Legos here or something like that, and they make a material called a polymer. The issue with polymers is that when polymers are produced, it is oftentimes extremely difficult to get them to break back down into monomers, there we go, or any other sort of biodegradable material. If we do choose to pursue that method, it often takes very expensive and very environmentally taxing resources to do so. So without this breakdown, though, they have the potential to exist for centuries at a time. I'll have you refer to the image on the right here, and this is exactly what Theo talked about earlier in the intro. These still aren't monomers. They're just really tiny bits of polymer that become an even bigger problem for us to take care of. That's not biodegradability. That's just a wider spread problem. And furthermore, there's a figure on the bottom of the screen here that exemplifies what a monomer looks like. What you're looking at here is nitrile, which is what most clinical gloves are made out of. And the bonds holding those two bracketed molecules together are very, very difficult to break down. And this doesn't come without a lot of environmental taxation, a lot of money, and a lot of time and resources. So we've made some progress in plastic chemistry throughout the scientific community, just based on the fact that we know that monomers really dictate how a plastic acts. So what we've tried to do here is tackle a couple different monomeric problems so we can get plastic to act different. Something that you guys are mostly familiar with, I'm assuming at this point, is something like a carbon reinforced plastic or a carbon fiber that often exists in the engineering world and any sort of civil engineering or aerospace applications. Now, carbon reinforced plastics are very, very sturdy. If you'll refer to the figure on the right here, that is a monomer for a carbon reinforced plastic. It is a big sheet, very scratch resistant, very lightweight, and they're very reusable, which means that they are already a piece of progression here in terms of recyclability. So we don't have to replace them often. They're very lightweight. They're extremely useful across lots and lots of fields. And ultimately, they're a really great step in the right direction in terms of not having to environmentally tax everything going on in terms of production. We're good for the next slide. But recycling is not always an option when it comes to plastics. Some things need to be single use. One of these things is PPE, which is why we are focusing on this problem, because it really can't ever be compromised as a reusable material. There are so many risks that are associated with that, from harmful material exposure per patient to potentially passing down illnesses. We can't stand to reuse examination or surgical gloves in these settings. So in order to address this problem of glove disposal specifically, we need to keep in mind the fact that these still need to be single use while taking into account some sort of environmental compromise that we can potentially make while looking at this material. So something that we've addressed earlier too is the fact that CO2 is copious in its emissions, and it's very big in problematic global warming issues. So if we are able to take consolidated and electrolyzed CO2, which we'll touch on in just a second here, and form it into a monomer that can be used to produce a plastic, that would be optimal in the sense that we're using something that is already very, very well existing and constantly emitted, and turning it into something that is potentially biodegradable and could replace things that are sitting in landfills for centuries at a time. So this is an infographic that we were able to track down through some of the literature that this group looked at. And essentially this spells out the process in a more visual setting so we don't have to keep throwing the words monomer and polymer around until we get to our endpoint here. So if you start on the right here, left here, we take a look at the CO2 emissions that are often produced from any sort of factories. I'm sure many are familiar with what this is representing. We are pumping CO2 into the atmosphere through extremely common terms of industrialization and things like that. Now there exists the chemistry properties in certain pieces of lab equipment. There are different instruments that are able to draw CO2 from the air and make it usable in a laboratory setting. So there is the potential to, in plenty of labs across the country, extract CO2 from the air and take it and use it in reactants in chemical settings. Now, I'm going to ask you to ignore the specific molecules that are sitting in the third part of this image here, because those are CO2-based monomers. They're just not the ones we're going to use. So we're going to table that for right now. But essentially what this is saying is we can use CO2 to make different compounds that are CO2-based. And furthermore, those can be used in all sorts of things across practical usage environments. Here it just highlights resins and furniture, plastics, and even the potential of pharmaceuticals, which is kind of the direction that we're trying to take this in. So one established candidate that we've been able to kind of dial down in the plethora of monomers that can be produced from CO2 is something called PPC. Now, PPC is something that we are using as more of a starting point right now because there is a lot of research about its tensile strengths and performance ability. Now, CO2 plastic as a developed concept is still relatively new. We don't have a ton on how all of this works quite yet because it is a pretty new concept. So PPC is a starting block for us as of right now with its high tensile strength. It has a fairly reasonable denaturation period because it is biodegradable, which is a step above where nitrile is at. The only issue with PPC is that it might be just a little bit, it's not quite to the point of where we can just use it to produce a plastic. It needs something called a plasticizer just to make sure that it doesn't degrade under normal conditions or direct exposure to UV or anything like that. So moving on. Oh, we got it, never mind. We are going to modify PPC, should we use it as a starting point, with isosorbide. So isosorbide is another molecule that is biologically derived. It actually starts with a cellulose molecule, which is found in lots of plants, trees, and other biologically derived sources like that. And this should increase the thermal stability and flexibility of PPC, which already has fairly decent parameters in that setting. So it still allows for breakdown, it just amps those parameters up a little bit more. So it's still not sitting in landfills for centuries, but it should theoretically make things safer in a healthcare setting. So essentially, to recap all of that, PPC plus isosorbide should equal a theoretical biological degradable polymer that we can use for gloves. So all of this should work out in a lab setting, right? We need to make sure before it ever goes into the healthcare system that it is something called biocompatible, meaning it is not compromising patient health and it's not compromising practitioner health. In order to do this, we need to make sure that it maintains its chemical integrity, which is the whole structure and function of the entire material before it is implemented into anything that would involve patient or practitioner risk. So what this would mean is essentially putting this into a lab, making sure that it goes through and passes rigorous tests that would test the ability for this to exist in ranging thermodynamic and biochemical environments. It needs to make sure that its mechanically strenuous properties are in place for being used in settings where it may be compromised. And once it's FDA approved, which is a pretty tedious process, it may move on to a manufacturing implementation.
Right. So as Abby has said, it does need to go through an FDA and also a CDC approval process. And this includes making sure that these gloves and the material are able to be used in medical settings. And so it doesn't put anybody at harm, both the practitioner as well as the person needing medical attention. But once this is approved, the material can be manufactured, and the manufacturing company that we would want to work with is called Associated Bag, and it is located in Milwaukee. Now, the main reason we want to work with Associated Bag is because our main goal is to start off with manufacturing and distributing the gloves in the state of Wisconsin. Additionally, Associated Bag is already making materials such as gloves, so hopefully this should be an easy implementation process. So if you look at the bottom, there is a material that the hand molds are being dipped into, and this is what makes the gloves. So our goal is that it would just be a quick and easy trade out for our material, and the hand molds will be dipped into it, and then it goes through a heating process, which then creates the gloves. Now, another benefit of working with Associated Bag is that they are also a distribution plant. So this is a one-stop shop for both the manufacturing and the distribution process. Now, if you look at the right at the map of the United States, you can see the 4 areas that Associated Bag is located in. Again, we would be working in the one that is in Milwaukee. And by the colors of the graph, you can see that the entire state of Wisconsin is in red. This means that it takes about 1 day for standard ground rates for the gloves to go from the manufacturing plant in Milwaukee to any place in Wisconsin. So this is also a quick and speedy way to get our gloves to wherever they need to go. Now, obviously, we are going to need to fund this project for both the development of the material as well as manufacturing and distribution. So our first stop would be working with the Environmental Protection Agency. This agency is a government program that is working with organizations and small businesses that are developing innovative ways and products that are environmentally helpful to making sure that we are reducing our carbon footprint and other environmental negatives that are occurring. We are hoping that we could get a grant from them because our project is trying to work towards a more environmentally friendly project. And they work with about $4 million per year and award that to different organizations. So we feel comfortable we would receive some amount of money, but also we would be working with the National Science Foundation because we hope we can implement this process into graduate labs so students can be working on this as well. And so it can be a learning experience. And there have been other projects such as the Emerging Frontiers in Research and Innovation, critical aspects of sustainability, and numerous other projects that have received funding. So we feel confident that we would be able to also receive funds from them. That being said, whatever is not covered, we are hoping to also apply to be a nonprofit organization in the beginning. This is so that we are legally able to accept monetary donations as well as other materials if we so need that we notice that we need them. So by having a nonprofit organization, we also hope that we can spread the word and hopefully get more awareness to what we are trying to do. But hopefully our end goal is to be financially stable enough where we can move away from being a nonprofit organization and actually start selling the gloves to different manufacturing plants, to hospitals so that they can use them, as well as even implementing them in stores such as Walmart so that the general public can use them as well. That being said, our main goal is to start implementing into the UW system. Now, the UW public health system is also tied to the education aspect of the UW system, but we are looking mostly at UW-Madison to start off with. This is because they've been a major player in COVID-19 developments, and even directly on their website, it says that they are looking to find new innovations that they can use to help them be better equipped to serve their community. And so because of this, we feel like they'd be extremely receptive and be able to market our solution. We also hope that these gloves could be used in the labs, the student labs, as well as health labs as well. And hopefully the students can be educated on this process, and this could be the new norm for how we use gloves in the future.
So just as Sarah said, this is going to potentially help to educate those on how this would be more beneficial environmentally, while also introducing something that may take the place of another compound that sits in landfills for centuries upon centuries. So some goals accomplished through the execution of this solution here is, for one, the environmentally friendly aspect of it. So it makes use of previously produced CO2 emissions instead of having to draw from things that are a little more copious to get our hands on. CO2, just as Brad and Theo brought up in the beginning, is in excess in our atmosphere, and it's not slowing down, which is disheartening, but it is currently true. Furthermore, this polymer that we would end up making is easier to biodegrade and therefore would reduce landfill volume from otherwise disposed of nitrile gloves. And ideally, this biodegradable material would not be necessarily harmful. It would be away from the microplastics, which, as Theo said, are extremely bad for wildlife, bad for the environment, and therefore bad for humans. And after that, I mean, it's a relatively simple implementation process. So ideally, once we get all of the lab parameters met, this would be something that we could phase into factory settings, which would preserve jobs. It wouldn't touch anybody's financial stability in terms of production. And most of those factors would remain constant, meaning we already have a network to work out of, especially if we were to pursue Milwaukee Bag. So this also opens various doors for other product development. Medical examination gloves are not the only plastic that needs to be single use for health reasons. Plenty of food packaging and other medical equipment, such as face masks or other things, also need to be single use in terms of preserving human health. So this could be moved into other fields of polymer chemistry, hopefully with some more research having to do with CO2-based polymers and everything else in that setting. So please feel free to ask any questions that may have come to mind during the presentation. The floor is open for you guys. All of our contact information is here. If you have any questions that you'd like to ask us personally, please reach out to us through these emails. Special thanks to Dr. Monroe Kroll for all of her fantastic help through this entire project. And a special thanks to Dr. Willoughby for some guiding words in terms of how polymers work. We really appreciate it, and the floor is your guys'.
Yeah, thanks to our group. If you could, audience, please feel free to put questions in the chat in Zoom. And excuse me, we're waiting for some of these. As we're waiting for people to put their questions in chat, I did actually have a question for you too. Oh, actually, we'll go with Professor Scanlon's first.
Yeah.
Did you investigate CO2 sources for making your isosorbital monomers?
Not for the isosorbital monomers. We mostly focused on the CO2 sources for the PPC specifically because that was already established. But that would be something interesting to look into. We started with the biodegradable source, or the biologically derived source, just because that was already established as a plastic. There were a few articles on how that itself was its own monomer. So we took that and we kind of ran with it in that sense, but that would absolutely be something to look into at a lab setting or chemical composition otherwise.
I have another question. The US government subsidized ethanol usage in fuels. Did you try to think of a way to have the government goose the use of these plastics, assuming that they will cost you more and that might hold you back? So in the way that there was an ethanol subsidy from the government, could the government do something similar with the use of these plastics?
Right. We didn't really take a governmental standpoint on this because we were more concerned with making sure the chemistry added up in the first place. But that would absolutely be another route to take this in terms of production. We haven't really looked into any sort of legislative side of this, just due to the fact that this would be going, first of all, into something that looks a little more like privatized healthcare. And I can see where that would come into effect when trying to market to a public university, and that would absolutely be another good thing to look into. But I'm not sure what the cost quotes would be there, but hopefully that would also be covered by the grants from the EPA or otherwise.
Okay, another question in the chat. What byproducts might form as the PPC gloves break down?
That's actually really dependent on other substituents that would be either connected to our other reactants. So I didn't state this outwardly in the presentation just for simplicity's sake, but we need to use CO2 and epoxides to essentially make this into a monomer. So that would depend on what kind of R groups were attached to that. Those could represent anything from other carbonates to some sort of phenyl group, but all sorts of things could go into that. So that would be a point of manipulation in the lab to figure out what would still serve for the best thermocompatibility and mechanical properties of these. But overall, carbonates have been approved to be hypoallergenic, and they are used in industrial settings. So ideally, it would break down into something that would not be toxic to humans nor the environment. But there is a figure in the paper that I was drawing out of in that sense. And if you would like to see that, I can absolutely get you that information.
Great. And another question. Going back to the slide about PPC modification. You talked about extracting cellulose from trees amongst other plant sources to supply your isosorbide. Wouldn't that make your processes less green if you are killing trees to make these gloves?
So I should clarify. We won't be harvesting necessarily live plants in order to do this. That would, in fact, you're correct, negate the process of trying to take a green approach to this. Cellulose is fairly common in non-living plants, meaning we would not have to go and chop down forests to figure out where this is. It can also be synthesized in a lab setting. So we can take anything from grass clippings to other biological materials to use this, meaning that honestly, we could draw from just about any sort of thing that includes cell walls in its cellular makeup. But otherwise, it can be synthesized in a lab. It's a fairly common material. So hopefully that gets rid of that concern.
Any other questions for the group? All right. Well, seeing none, I want to thank everybody for coming today, and I want to thank our presenters. They did a lovely job. Thank you all very much. And I would encourage you all to go on and attend one of our last Catalyst Day sessions. There's a separate Zoom link for each one that you can find on the website under Catalyst Day. So again, thanks to our group for presenting, and thanks to everybody for attending. Have a good afternoon.